we got to determine what exactly a Newton is. Newton is a unit of force. Okay, so that's the one we're going to be using in this class. Okay, so, of course, force with Newton's second law is mass times acceleration. Okay, so for example, in my case, if you take my body, I'm exerting force onto the ground. Okay, I'm just standing here. Gravity's pushed me back up, but I'm putting down force down. What is that force? Well, we know force equals mass times acceleration. So if I plug in those numbers, force, mass, times acceleration, my mass in kilograms is 91, so 91 kilograms, times my acceleration due to gravity, because we're here on Earth, that's 9.8 meters per second squared. If you multiply those together, it comes out to be 892. Now it would be kilograms meters per second squared, and that's 892 big N, which stands for newtons. All right, so that's the force I'm pushing down on the ground, and of course it's pushing me back up. In a minute or so, we may be showing a demonstration with these kilogram masses being suspended by, it's a kilogram mass right here being suspended by a string. We're also going to use half a kilogram, and here is a 0.25 kilogram. So if we need to figure out what that force is, okay, it's hanging on a string. Okay, so that force for that small little mass there, again, force is mass times acceleration. The mass of this is just 0.25 kilograms, and of course acceleration is 9.8 meters per second squared. Okay. If you do the math on that, it comes out to be 2.45 newtons. Okay. And of course, if you did this one here, half a kilogram, this would be 4.9 newtons. And of course, with 1 kilogram, that's simple, 1 times 9.8, so this would be 9.8 newtons. Okay? So that's the unit of force we're going to be using in this class. Okay? So, all right, this time I've changed one of the variables. Okay, instead of it going across a nice smooth table, it's going to go across this little pink towel. Okay, so let's see what happens this time. All right, so understandably, there's more friction, so it slowed it down. Okay, it got it out to about 62 or 63 centimeters before it stopped. So now if we look at that distance versus time graph, instead of going straight across like that because of the friction, okay, the distance increases to about 63 and then it stays at that distance, so it would level off there. If we look at speed versus time, of course as soon as it hits that the towel, it starts slowing down, so it's deceleration, and until it gets just over half a second, it probably goes to 0. All right? So that's what it would look like when it would come to a stop.